Here we'll have discussion, this type of the question, what they're asking, like discuss or explain about power transmission, or you have to calculate the power loss. So that we are going to see what are the different types of the losses. Before that, we are going to see how power transmission will take place in the rectangular waveguides. So this type question they have asked many times in the regular as well as supply exam also. Okay, explained about different types of the power loss in the rectangular waveguide and sometimes about power transmission. So if you didn't subscribe our channel, please subscribe it, share with your friends so that maximum people should get benefits. So here we are got already we have seen before this about rectangular waveguide. So the dimension of the rectangular waveguide we have, this is along the x-axis, this is A, and this one is along the y-axis, that width or height is the B here, and this rectangular waveguides can be seen in this way. Okay, so already previous lectures are available in the playlist. So here we are considering that in general, that when maximum power will be transmitted to the load. So here we are going to consider like you have maximum power transfer theorem, that load impedance and Thevenin's impedance are going to be equal. In case of when we will talk AC, it's going to be conjugate of each other. So here we are considering that waveguide that end is terminated, like meshed termination we have in the lab. You can see that it is terminated such that there will be no reflection is going to occur, so that whatever we have transmitted, maximum is going to reach. Or we are going to consider that it is the waveguide is long enough, okay, in compared to wavelength. So these two assumption is done here to calculate the power transmission. And now we are going to use the Poynting theorem. So in Poynting theorem, we are going to use the Poynting vectors. So the transmitted power by the help of Poynting vector is given as integral of Poynting vector over the closed surface. Okay. So this is the Poynting vector, that integral over the closed surface. And finally, that vector is given as 1 by 2 E cross H. So H conjugate is here. So this is the general expression how we are going to calculate the transmitted power. So now we are going to consider lossless dielectrics. Lossless dielectric means conductivity. If it is a perfect dielectric, then conductivity will be 0. But it is a lossless or lossy type means yes, somewhat conductivity we can achieve. So in case of lossless dielectric here, the time average power flow through the rectangular waveguide is given as 1 by 2 ZG. G is here for the waveguide. Integral of modulus of E square, okay, dA. Or if you want to write in terms of magnetic field, so it is going to be ZG by 2 integral of H square with respect to dA. So what is the ZG here? It is EX by HX. Or if you see in case of Y components, it is we have minus EY by HX. So like in general, if you talk about intrinsic impedance, so there we have ratio of E by H on the basis of similar concept. This ratio we have for this waveguide. So this E square, modulus of E square is the modulus of EX square plus EY square. Similarly, modulus of H square is the modulus of HX square plus modulus of HY square. Now we are going to talk about the modes. So already we have seen that we have a general discussion, and we have seen that T10 mode is going to be dominating mode here, and where M will be 1 and will be equal to 0. Okay, so first we are going to see the general discussion. If it is TEmn modes, so any value of Mn for that T mode is going to exist. So that transmitted power in terms of cutoff frequency and intrinsic impedance are given as we have root under 1 minus Fc by F whole square. Okay, and F is at particular frequency. By numerical will have more clarity about this. Divide by 2 eta. Now we have E is replaced by, okay, this value that we have earlier, modulus of E square. For that we are writing in terms of Ex and Hy. and length of one side of the rectangular waveguide is going to be 0 to A, and one side is going to be 0 to B. Along the x-axis, 0 to A, along the y-axis, 0 to B. And it is being integrated with respect to dx and dy. So similarly, in case of transverse magnetic field here, TMmn modes. So now a small change will be here in the formula. So what we have root under, so that become here in the denominators. So we have 1 by 2 eta into root under 1 minus fc by f square. And again, this integral parts 0 to A, 0 to B, and these parts remain same. Only this portion has this parameter has changed here from numerator to denominator. Where this eta is what? That already we know. It is root under mu by epsilon, which is called as intrinsic impedance of the unbounded dielectrics. This is a consideration for the unbounded dielectric here. So that is how power is being transmitted in case of rectangular waveguide. Now, main important thing is power loss. Okay. Any doubt will be there, you can write in the comment box. So power loss. So what are the various losses are going to occur in the rectangular waveguide? So these losses are characterized as loss in the dielectric and loss in the guided walls. So this guided walls through which wave is going to propagate, there also loss is going to occur as well as in the dielectric. So first we are considering here loss in the dielectric. So in the lossless, when we'll talk about low loss dielectric, like we have lossy dielectric. So here conductivity takes place, but conductivity is much smaller in compared to mu epsilon, that is called as the low loss dielectric. So for this propagation constant for any plane of wave that is going to travel in unbounded lossy dielectric, okay, is given as, so lossy dielectric means it has some conductivity. If you talk about perfect dielectric, that conductivity will be 0. So alpha, that is here we are talking about the attenuation. So alpha equal to sigma by 2 root under mu by epsilon, and root under mu by epsilon is the eta. So finally it is written as eta into sigma by 2. Now if you talk about in the different modes like TMN modes or TMmn modes, we have considering here low loss dielectrics, then inside the waveguide that attenuation alpha g is given as sigma into eta by 2 root under 1 minus fc by f square, where fc is the cutoff frequency and f is the any frequency at which we are going to calculate. So this is expression for T modes. And again, now in TM modes, we have alpha g equal to sigma eta by 2. Now this term came to numerator, so that is root under 1 minus fc by f whole square. So when we have calculated the transmitted power, this term under root term was in the numerator in case of T modes, whereas this term was in the denominator in case of TM modes. But here it is just opposite of that. Now, if this given frequency is much greater than the cutoff frequency, then you can see that what will be the value of here. So attenuation constant in the guide approaches as we have seen in the equation 1. Okay. So since here f is much greater than fc, so finally when we divide here, this term is going to be cancelled. So finally we'll have root under this, we'll get the root. So this 1 minus fc upon f. So this is going to become the value root 1. So we'll get the 1. So that's why similar expression we are going to get as the equation 1. Here we'll get sigma into eta by 2. But when f is much smaller than fc, so in this situation, what will happen here? So that term inside that square root, the second term here we can't ignore since f is much smaller than fc. So that we are not able to ignore here. So finally it is going to be subtracted from 1. So that's why this alpha g value is going to become very large and no propagation is going to occur. So condition for the propagation, f frequency should be much greater than fc. Okay. And when it is much lesser than fc, propagation is not going to occur. So previously we have seen different conditions when the propagation is going to occur. In the different lectures are available that you can see in the playlist. Now we are talking about losses in the guide walls. So just now we have seen loss in the we have seen in case of dielectric. Now we are seeing inside the waveguides walls. So when electric field and magnetic field intensities both are going to propagate in case of lossy waveguides, so their magnitudes we can represent. So here lossy waveguides means propagation will occur. So here we have electric field modulus is given as EOZ e to power minus alpha GZ. So G is for the waveguide and EOZ is and HOZ are the field intensity at Z equal to 0 when we are going to start. Similarly, modulus of magnetic field is modulus of HOZ e to power minus alpha GZ. So in case of now, if you see here, in case of low loss guide, the time average power flow decreases proportionality to the, if you are trying to, like we have seen in case of transmitted power, so that what we have E into H, okay, by using the Poynting vector. So finally this e to the power minus alpha GZ and e to the power minus alpha GZ both will be added together. So we'll get here e to the power minus 2 alpha GZ. So this transmitted power, okay, so that some power is being lost here, so that is also considered. So PTR plus P loss e to power minus 2 alpha GZ. So that is power is going to be decreased by this factor, okay. So now if transmitted power loss is much smaller in compared to transmitted power, and this exponent power 2 alpha G into Z is again smaller than 1, then we can write the expression. If it is much smaller means that all we can ignore or we can make rearrangements. So some expansion we can apply. Then we have P loss by PTR plus 1 this side and here 1 plus 2 alpha G into Z. Okay. So now finally this 1 will get cancelled. So we have P loss by PTR equal to 2 alpha GZ. And from here, we got the alpha G value, that is the P loss by 2Z PTR. And finally, it is written as PL by 2 PTR. So PL is what here? Loss per unit length. That is the given as the PL. And P loss is the complete loss and PL is the loss per unit length. Now we have to find this PTR value already we have, and if you obtain the PL value that we substitute in the equation 7, we'll get the alpha G value. So what we are seeing that field intensity is going to decay exponentially, okay, where at the surface with respect to skin depth while the waves progress into the wall. So already we have discussion about the skin depth also in case of electromagnetic theory. So separate lecture is there in the course of EMTL, okay. So that skin depth means it's showing the penetration, how far wave is going to penetrate to that wall, okay. So finally, surface resistance of guided wall is the rho by skin depth here. So 1 by rho is what? 1 by sigma. So 1 by sigma into skin depth, that is the del. And this is alpha G by sigma. And already we have expression for the skin depth, 1 by root under pi r mu sigma. So after rearrangement, you are getting root under pi r mu by sigma. This is the ohm per square. This is the surface resistance of the guided wall. So now we have power loss per unit length, which is given as PL equal to RS by 2, okay, integrals of modulus of HT square into DS. So that is watt per unit length, where HT is the tangential component of the magnetic field. So now we got the value of PL, already we have value of PTR, so those values are substituted in the equation 7. So finally we have alpha G value RS into surface integral of modulus of HT square into DS divided by 2 into ZS integral of modulus of H square over the dA. Okay. So now finally, where already we have seen in the previously also modulus of H square is here modulus of HZ square plus modulus of HY square in this case. And here tangential component modulus square is the modulus of HTX square plus modulus of HT y square. So that is a small difference is here in both. So this is how this is the loss is going to occur. Okay, this is the factor alpha G. So due to which by which fact this factor there is the decay exponentially. So like this we have explanation about two different types of the losses. What are the losses? Dielectric loss and waveguide loss. So this question is very important. Now we can see one small numerical based upon this. If question is little twisted, you'll get the problem. So it is a numerical and airfield waveguide with cross section. That is cross section is given. That is the dimension of the rectangular waveguide 2 cross 1 centimeter. Transport the energy in the TE10 mode. That is the dominant mode here at the rate of 0.5 horsepower. The impressed frequency is 30 gigahertz. So here F value is the 30 gigahertz. What is the peak value of the electric field occurring in the guide that we need to find? So here TE10. So what is the mode here? That is TE10. So M is 1 here, N is 0. So we already know what is the M and N. Okay. So in this situation, we have EX equal to 0 and EY component is EOY sine pi X by A into e to power minus j beta gz. So here M is going to be equal to 1. That's why here in place of this value is 1. Ez is what? 0. Similarly, magnetic field components, we have EOY by ZZ. ZZ sine M pi X, so M value is 1, A e to the power minus j beta g z. So we have components, that is the N pi Y by B. So here what you're saying, N is 0. So that's why that component is not available here. Now similarly, HZ equal to HOZ cos pi X by A e to power minus j beta g z. So A is the dimension of the rectangular waveguide along the x-axis, where Zg is what? Omega mu naught by beta g. So these are the from the derivation, previous derivation. Okay. So here now we have a phase constant value, that is the expression beta z is here. So like in attenuation, we have propagation constant. In that we have one attenuation constant, that is alpha. Another is the beta is the phase constant. So here we are talking about the waveguide. That's why using the G here. So that expression is root under omega squared into mu naught epsilon naught minus pi square by A square. So now omega is 2 pi f. Okay. So finally, after simplification, we can write in terms of velocity of light. So 1 by root under mu naught epsilon naught is what here? Velocity of the light. On the basis of that, we are writing the expression. So finally, pi is taken common here. So that is taken outside and divided. So we are getting this expression. Now we have frequencies 30 gigahertz. So 30 into 10 to the power 9. And C is the velocity of light. So 3 into 10 to the power 8 meter per second. And dimension is given 2 cross A. So 2 is the A is here 2 and this is the B. So that is in centimeter. So it is converted into meter. And after that, substituting the value by calculator, you can calculate. It is 608.81 radian per meter. Now, power delivered in the z direction by this guide, we know for that expression. So from here, we can find the value of E0y. What they're asking, find the peak value of the electric field occurring in the waveguide. So that peak value, we have to find the E0y. So this delivered power, real part of this 1 by 2 integration over 0 to B, 0 to A, and here E cross H star dx dy and mu z. So now we have substituted the value of E electric field component here, and for the H dash H star conjugate, we have substituted the value. Okay, and by substituting the value of ZG, we are getting this portion. And this is the conjugate. So this we got here minus, and this exponent become the plus here. And after that, simplification is being done. Addition, whatever, like here e to the power minus j, here e to the power plus j, that will become e to the power 0. So e to the power 0 is 1. And what are the common terms that we are taking here out? So E0y is coming 2 times. So that is multiplied. So square outside. Beta g by omega epsilon naught is taken outside here. Okay. So all this simplification in this consideration is done here. So now if we substitute the value, okay. So integration of this, and we are substituting the value. So we are getting here beta g by omega mu naught into AB. AB is what here? Dimension. So now once you substitute this value, what are values are given? So we are getting EOY equal to 53.87 kilovolts per meters. So these are the how we are going to simplify. Here, what are the expressions are given that we need to utilize. Okay. So this formulas, what we are going to derive at last, those formula is important. On the basis of that, we are going to find the expression. So now finally, in general, if you want to talk why TE10 mode is important, okay, for the extra information. So here, if you see antenna probe connection, this is length is here in terms of wavelength, that is lambda by 2. That is A is given in terms of wavelength. This is the exciting TE10 mode in the rectangular waveguide. So here you are seeing that connections, okay. Now, similarly here in this situation, what we'll see, one antenna probe is here, one antenna probe is here. So this for the probe 1, it is in phase. Okay, that is shown by this arrow direction. For the probe 2, it is out of phase. One is moving left, one is the right, and both are separated by the distance lambda by 4. So, okay, so here RF input is given. So then how we are able to obtain. So this is how we are able to launch the TE10 mode in one directions. So these are the discussion, and other lectures are also available in the playlist. Any doubt is there, you can write in the comment box, like, share, subscribe. Okay, so that maximum people will get benefit. Thank you. Thank you very much.